Hey everyone. So today in this video and a series of video that will follow this video, we will be emphasizing a lot on DSU. DSU means Disjoint Set Union, and it is one of the most fascinating data structures. Before I begin, I would like to give you a brief introduction about myself. I have a major in computer science and I have solved more than 1300 problems on LeetCode. And based on problem solving skills, I rank globally in less than top zero point 0.3. Okay. Apart from that, I have a very solid research interest in statistics and machine learning, and somewhat and a very curious interest in medical science as well. For example, I also interned at MIT, where my area of focus was in statistics and machine learning. Yeah, so that's it about me. Now, one of the reasons why I am making this series is because I want to deliver you a very clear, intuitive, and a very in-depth approach, the kind that is not narrow, but it would help you to tackle a lot of real life challenges, problems. And one thing that I would like not to do is to make this series a very narrow and entirely focused on lead code. But my goal will be to, by the end of this series, my goal will be to inculcate a scientific temper within you so that you start to think like a computer scientist. You start to think like somebody who loves computer science and mathematics. Okay. So, yeah, with all that, now let us begin this series. Before I begin, let me tell you what we will accomplish after the end of this series. So, the first thing that we will accomplish is that we will be able to understand the core operations that is available in DSU, and those are the find operations and the union operation. We will also understand DSU in a very in-depth manner and in a very optimized manner through path compression technique and ranking by and a union by rank. We'll also be able to solve problems based on minimum spanning tree through Kruskal's algorithm. We'll also tackle cycle detection, and we will also tackle problems based on connected components. Okay. Now, since the name implies disjoint set union. Okay. So I think it is very imperative of me to discuss about all those three things in separate way. Okay. So first of all, as you can see, this is our universal set here, and we have four different components which are not interconnected with each other, as in they do not share any common elements within each other, right? So when a set do not share any common component with other set, then we say that that set is independent of other set. Okay. For example, this set is disjoint from this set, this is disjoint from all these three, and so on and so forth. All of these sets are disjoint, and we can even draw a hypothetical boundary in this universal set of ours, something like this. This boundary belongs to that, and similarly for all other boundaries. Okay. Now, let us start our journey. And in this way, and in this video, I'll be giving you a very overview of DSU. Okay. So before I begin, I think it is again imperative of me to talk about a few terms, and I would like to clarify those. The first is parent and the other is children. So what is a parent? Parent is a node that has descendants node attached to it. Okay. For example, in this case, 0 is a parent and it has 1 and 3 attached to it. Okay. But what is a children then? So children is a node that has a parent. Or in other words, children is a node that is a descendant of other node. For example, is 8 a children? Yes. Why? Because it is a descendant of 5. Okay. Is 7 a children? Yeah, it is. Why? Because it is a descendant of 4. Is 9 a children? No, it is not, because it is not a descendant of anything. Okay. So in this case, 9 is not a children. All right. But then what is a sibling? Siblings are those nodes that have a common parent. Are just a second. Yeah. Are 8 and 9 siblings? Are 8 and 6 siblings? Yeah, they are. Why? Because they have a common parent as 5. Okay. Are 3 and 2 siblings? No, they do not. Why? Because the parent of 3 is 0, while the parent of 2 is 1. Okay. Is 9 a sibling? No, 9 is not a sibling. Why? Because we need another node. We cannot have an independent singleton sibling. Okay. So whenever we try to compute sibling, we compare with more than one nodes. Okay. For example, is 7 and 8 siblings? No, they are not. Why? Because the parent of 7 is 4, the parent of 8 is 5. So their parents are different. So they are not siblings. For siblings, their parent must be same. All right. But then, what is a root? Okay, so root is such a node that do not descend from anywhere. Okay, but in fact, root can have lots of descendants. For example, in this case, 0 is a root because it do not descends from anywhere, but it has a lot of descendants. Okay, 4 is a root. Is 8 a root? No, it is not. Why? Because it is descending. Okay, is 9 a root? Yeah, 9 is a root because it do not descends from anywhere. Okay, that's it. So I think I have cleared out some of the important terminologies, and I hope these things are cleared. Okay, now since we are taking a very brief overview of how DSU works, so why not better just look at their operations, common operations, and try to get a sense of how it will look like as we move forward. Okay, so first of all, let us try to do this union operation. Okay, so we have this graph over here, okay, these separate nodes over there, and we'll try to bind them using this union operation. The first one is, hey, can you please fuse 0 and 1? So every time we are adding to node or every time we are connecting to nodes, we'll consider one of the node as root and we'll attach the other node to the root node, okay? For example, in the case of 0 and 1, we'll consider 0 as a root and we will create a set, something like this, okay, where we have 0 and 1. All right. Now, hey, can we connect 0 and 3? Let us connect it. We have 0 over here. We have 3 over here, okay? Let us consider 0 as the root for 0 and 3. And let us add 3 to this set. So this will look something like this now, okay? So this is a new set. Hey, can we add 1 and 2? Let us do that. The root of 1 is 0. Let us consider the root of 2 to be 0 itself. So in that case, when we will fuse it, it will, just a second, yeah. It will become something like this. This will be our new state, okay? Okay, can we connect 4 and 7? They are not connected now. So let us consider 4 as the root and let us fuse 7 with it, and we got a different state, okay? Hey, can we connect 5 and 8 or 5 and 6? Let us connect 5 and 6 first. Let us assume 5 to be the root, and let me connect 5 and 6 together. Hey, let us connect 5 and 8. Let us assume 5 as the root, and let us fuse 8 to that. So it will look something like this. Just a second. Okay. So if you look at this thing, it looks pretty much identical to what we have above. We have this component and we have this entire set component, correct? We have this component and we have this component. We have this component and we have this component. And we have this independent component and we have this independent component. Okay, cool. So now let us take a look at one of the important operations that is in DSU, where we try to find or ask ourselves, hey, are the two nodes connected? Okay. In fact, throughout our series on DSU, in fact, like DSU, one of the main question that DSU targets is that it answers the questions regarding connectivity. Okay. So let us ask ourselves, hey, is 2 and 3 connected? Okay. Let us look for the root of 2. The root of 2 is 0. Okay, the root of 3 is 0 again. So if we have a similar root, then we can say yes, 0 and 2 and 3 is connected, which is pretty much obvious because if you take a look at this thing, it is asking, hey, 2 and 3 connected. Yeah, it is connected because we can traverse like this, correct? All right, cool. Uh, hey, is 7 and 8 connected? Okay, let us look at the root of 7. It is 4. And let us look at the root of 8. It is 5. Okay, whenever I'm taking a look at whenever I'm taking a look at the root, I'm just looking at the set and I'm looking at the root. Okay, so since the roots are not equal, so we say that, hey, 7 and 8 they are not connected, which is again pretty much evident because 7 and 8 they are not connected. We cannot go to 8 or we cannot come to 7 because they are two independent separate components, correct? Now we again ask ourselves, hey, is 9 and 9 connected? Okay, let us see. The root of 9 is 9 itself. So yeah, 9 and 9 is connected, which is again pretty much similar, which should be obvious because we can, from 9, we can come back to 9, and from 9 again, we can come back to 9 again, okay? Is 5 and 8 connected? All right, let us take a look. The root of 5 is 5, the root of 8 is 8. So the root is, sorry, the root of 5, where is it? Oops, just a second. Okay. Mhm. The root of 5 is 5. The root of 8 is 5. So we say, hey, 8 and 5 are connected. Again, it is obvious because 8 and 5, they are connected, correct? So this is how DSU looks like. Once again, the one of the most imperative question that DSU answers is regarding connectivity. So yeah, um, we'll take a look at how these operations of union and is connected works and how we can optimize it. And there are lots of ways. Okay, so let's go to the next slide. Now in this slide, I will be trying to implement DSU using the array. Let me just unhide all these things first for the better clarity. Okay. Now let us take a look at what is going on here. We ask ourselves, hey, can we union 0 and 1? Hey, let us union 0 and 1. Okay. So 0 and 1 we have here. When I union this thing, let me make 0 as the root, and we come over here and change the parent value of 1 to be 0. Okay. By the way, this whenever I'm trying to implement DSU, we need to maintain a root array, or in some cases parent array, and its vertex will be represented by the index, and the values present in this array will either represent the parent or either it will represent root. When it will represent parent, when it will represent root, we'll see that later on. Okay. For in this case, for in this specific case, it is representing just the parent. Okay. Now, hey, let us connect 0 and 3. All right. So in this case, I'm assuming 0 to be the root again. Let us assume 0 to be the root for 3, and let us connect it. So I'll come to the array. I will change the vertex 3 value to be 0 because 0 is the parent according to this connectivity. Okay. Hey, let us connect 1 and 2. So when I'm connecting 1 and 2, let me consider that the parent of 2 is 1. Okay. So I'll come to this value part array, and I will change it to 1. Okay. Now, before I proceed further, I would like to emphasize a bit on this connectivity that we have formed here. Okay. How do we answer this question of whether 2 and 3 are connected? We answer that by looking whether they share a common root or not. In this case, it is pretty much visible that root of 2 and 3 is 0 and they are connected. But how can we fetch that information through the arrow, no, through the array? Yeah. So let us begin from here. We have to answer whether 2 and 3 are connected or not. So we go through 2. We see that the parent of 2 is 1. So we go back to 1 and we see that the parent of 1 is 0. So we come back to 0 and we see that the parent of 0 is 0. It means the 0 is the root for 2. Okay. So the root for 2 is 0. Similarly, we start from 3. Similarly, we start from 3 and we go back to 0. Why? Because the parent of 3 is 0. We go back to 0 and we see, hey, 0 is a root for itself. So in that case, the root of 3 will be 0. Okay. So we see that the root of 2 is 0, the root of 3 is 0 since they have the common root. So yeah, it is connected. Okay. Now let us try to union 4 and 7. We union like this. We come to 7 and we change the value to 4 as because 4 is the parent for 7 now. Hey, let us union 5 and 6. So we union 5 and 6, something like this, and we consider 5 as the parent for 6. We come to 6 and we change its value to 5. We union 5 and 8. We consider the parent of 8 to be 5. We come to 8. We change the value to be 5. Okay. Again, yeah. So let us ask ourselves a question. Hey, is 7 and 8 connected? It is visible from the graph that they are not. But how do we answer that question? We answer that question by looking at the root of those 7 and 8. Okay. All right, cool. So let me take a look at that. Hey, let us find the root for 7. All right. We go to 7. We see that its parent is 4. So next step, we go to 4 and we see that the parent of 4 is 4. Okay. So in that case, the root of 7 is 4. Now, we ask the same question for 8. We start from 8. We see that the parent of 8 is 5. So we go to 5 and we see that the parent of 5 is 5. And when that happens, when the parent is equal to the root itself, so we say that that is the root. Okay. So in this case, the root for 8 is 5. And since 4 is not equal to 5, so it means that they are not connected. Okay. So moving forward, in the next lecture, we will take a look at the find operations, and also we will take a look at the union operation in depth. Find operation is an operation which will help us to determine the root or the parent, depending upon how we are trying to approach our problem. And union operation will help us to connect components or nodes. Okay. Again, find operation is a very interesting operation. So is the union operation. Find operation, it will help us to determine the root of a node, and the union operation, it will help us to connect the nodes or connect the component. Okay. And just to be clear, in this case, every time the vertex is and it's equal to the array value, correct? For example, in this case, 5 and 5 are equal. So we say that, hey, 5 has a root of 5 itself. But take a look at this case, 2 and 1. Okay. So we say that since these are not equal, so we say that the root of 2 is not 1. So in order to find the root of 2, we go to the parent of 2, which is 1. When we come to 1, we again take a look at its value, which is 0. We go back to 0, and we see when we are at 0, we see that the value of 0 is equivalent to 0. Okay, so we say that the parent of 0 is 0. In some sense, it is like a continuous ascending. Okay, continuous ascending, just go through the value, explore, and stop only when the value of the array is equivalent to the value of the index. The index is vertex, and the value is the value of the parent. Okay, and when that happens, it means we have found the root, and we stop. Okay. So yeah, so this was just a very basic overview of how DSU looks like and the operations that are available in DSU. Moving forward, we'll try to explore and we'll try to optimize the operations, and later on towards the end, we'll try to code it and we'll try to solve a real life example. With that, thank you, and I'll see you in the next video.